were discussing the equivalent lateral force procedure for seismic analysis of building structures, and in that we have already discussed several of its important steps, and let's quickly summarize it and actually finish this topic now. So we started with how we can calculate the approximate fundamental time period of your structure, and then the steps to determine the design base shear, right? And then finally we were here where after the vertical and horizontal distribution of base shear, we had some additional considerations. For example, considering the inherent and accidental torsional moments in the analysis, and the summary was that inherent torsion is automatically accounted. For accidental torsion, you have to provide an eccentricity, and that eccentricity is used to determine that accidental torsion. So this is that provision about eccentricity, that if you are applying forces in x direction, 5% of the eccentricity, 5% of the diaphragm dimension in the perpendicular direction should be considered as an assumed eccentricity between center of mass and center of rigidity, right? So this 5% is a caudal provision, and it is considered adequate to account for any accidental you can say moment which can occur during the design life of your building. There is an upper limit on that accidental torsion also. If your building is qualifying for the irregularity type 1A, 1B, and if it is located in seismic category D onwards, then you have to amplify that accidental torsional moment with an torsional amplification factor, and the value of that factor will be this one. So obviously your delta max will be more than 1.2 times of delta average in order for your structure to qualify for that type 1A, 1B irregularity. So obviously this AX will be greater than 1 if you fulfill that condition, and then you need to repeat the analysis by multiplying that amplification factor with your torsional amplification, accidental torsional moment, right? So then the next step is the story drift determination, that you have to actually ensure that the story drifts they are all less than an allowable value which is coming from this table 12.12-1. So how you calculate story drift? That first you calculate the story displacements when you apply the design forces which are already reduced with R. So you apply F1, F2, F3, Fn, and then calculate elastic displacement caused by those reduced design forces. Then you amplify those elastic displacements by CD over I. So each of the story displacement is now being multiplied by CD over I. So first story displacement, second story displacement. So we get the amplified displacements corresponding to the solid line deformed shape here. And then we calculate story drifts from those displacement. Drift is defined as the relative deformation of one story relative to other. So upper story minus lower story displacement will give you the drift. So capital delta is the drift for second story. For first story, obviously the upper story is the first story, lower story is the fixed support, so will have zero displacement. So you calculate the drifts like that. So these are story drifts, and if you divide them with the story height also, they are called story drift ratios, right? So inter-story drift ratio or story drift ratio is when you divide that story drift relative displacement with the story height also. So second story drift is divided by second story height L2, and first story drift is divided by first story height. So you will get the story drift ratios. The allowable limit is in the form of story drifts, right? So that is the next step, that you check that the story drift of each story is less than the allowable value prescribed by the code, right? So it's like you design for forces and you check deformations, right? That's why it is called force based design. There is an alternate design philosophy also called displacement based design, in which you start with an assumed design displacement or calculated design displacement and then calculate back those forces which will be produced in your structure when it will undergo that displacement, right? And then make sure that the enough capacity is available in all the elements to handle those forces, right? And ultimately this will ensure that the elements will handle those displacement, design displacement, right? That is a separate design philosophy called displacement based design. But currently the conventional code based design is called force based design, because the main design variable is the design force against which the capacity in the form of force is provided. So you calculate an mu, for example, and provide mn against that, right? The maximum design action in the form of force is calculated and the capacity in the form of force is provided, mn, right? Similarly, vu will be provided with a capacity vn, tu with tn, axial load pu with pn, right? So in force based design setup, you just check that the deformations are less than some allowable value. So the role of calculating deformations is this one, that only checking that they are less than allowable. So you go to that table and you will see that depending upon the type of structure and depending upon its risk category, there will be an allowable delta value which is prescribed, let's say 0.002 or some other number, right? And you have to make sure that the story drifts, they are less than this allowable value, right? There is an additional requirement that if you are having a moment resisting frame in the seismic design category D through F, then you have to divide that allowable value with a redundancy factor, and the procedure to calculate that factor is prescribed in this particular section, right? So if you fulfill this criteria, then you have to divide delta A allowable value with an additional redundancy factor. So you have to check with a more strict, you can say, allowable value. Then another important consideration is the consideration of P delta effect. First, the recommendation is that you don't include it in the analysis, and then as part of this requirement you check whether you need to include or not, right? So the procedure is that you need to calculate a stability coefficient, this one, which is denoted here by this theta. For each story you will determine this value, stability coefficient. This will tell you that whether you need to include P delta effect or not, right? So the expression for calculating this stability coefficient involves the vertical design load at and above that particular story for which you are calculating that theta. Delta is the drift from ELF, and which is already multiplied by CD over I, amplified drift of that story. I is already there, CD is already there, you know. Vx is the story shear force acting between level x and x minus 1. So that story and one lower story shear between that. HSX is the story height below level x. So it's like if you closely look at this expression, it is the ratio of two moments, right? P into delta and Vx into Hx, right? So it is the ratio of secondary moment, P delta moment, with the overturning moment at that story, because Vx is a lateral force. When you multiply it with the height below that story, you will get a moment which is an overturning moment, right? It is a moment which is trying to topple over your building in lateral direction, right? And Px is the axial load and delta is the lateral drift caused by the lateral forces. So it is actually a second order moment, right? P into delta, right? So it is the ratio of two moments, a moment which is second order moment and a moment which is trying to overturn your building. So this ratio will actually tell you whether actually P delta effect is significant or not, right? So you calculate this ratio or this theta factor for each story. Vx is the story shear profile. It will come from the story shear against the lateral force. So if you have, for example, 3-story building, so you will calculate 3 forces as a result of this ELF procedure. So you can simply plot the story shear profile like this, right? It's just like the SFD or story force shear force diagram of just one cantilever column, right? So first force, then it will be constant, then second force, third force, right? Similarly, story moment also you can plot like this. Obviously it will be highest at base and lowest at top. So Vx will be coming from that story shear profile, this one, and Px is coming from the vertical design load combination, right? Gravity load combination. So Px you need to extract from the analysis program, right? So whatever is the axial load on that particular story, and delta is the result of the application of ELF forces, right? But they are already multiplied with CD and I, so you need to consider that also. The expression is set such that these capital delta is already amplified value, right? So let's say that you calculate that delta theta factor for each story, and if theta is less than 0.1, which means the second order moment, additional P delta moment is less than 10% of the overturning moment, the P delta effect on all demands are not required to be considered, right? So if you found out that theta is less than 0.1, no need to repeat the analysis or modify the results while considering P delta, right? By the way, there is an upper limit on theta also. I'll explain that at the end. Then second case is that okay, now I think I should first explain theta max because it is there. So there is a maximum value of that stability coefficient also, which is 0.5 times beta into CD, and it should be less than 0.25. Beta is the ratio of shear demand to shear capacity for that particular story between level x and x minus 1. You can conservatively take it as 1, but actually beta is shear demand Vu over Vn of that whole story, right? So if you have like a capacity which is 2 times of the applied shear or demand shear, then your beta will be 0.5, right? But in no way it can be less than okay, so it should be less than 0.25. It cannot be the theta max value cannot be greater than 0.25, right? Conservatively you can take this beta value equal to 1, which means that demand and capacity can be conservatively assumed as equal, right? So if you want to just remain conservative, no need to calculate the actual beta, just put 1 and CD value, you will get a theta max. Now if your actual theta of your stories is between 0.1 and theta max, right, upper limit 0.1 and upper limit, the incremental factor related to P delta effect on displacement and member forces shall be determined by the rational analysis, or you multiply displacement and member forces by just 1 over 1 minus theta, right? Let's say your theta max comes out to be 0.2 and your actual theta which you calculate for your story your story is 0.15, somewhere between 0.1 and 0.2. Then you calculate an amplification factor 1 over 1 minus 0.15, right? 1 over 1 minus theta. That amplification factor, obviously this will be greater than 1. You multiply all the displacement and member forces by that factor, amplify them to account for the P delta effect, right? Alternatively, you can use some rational analysis also, some analysis procedure which explicitly can calculate second order moments or explicitly account for P delta analysis, right? So if you check the automated option of including P delta analysis available in the commercial structural analysis programs, then no need to amplify manually, right? Just check that option P delta and it will automatically account for any potential amplification in the member forces and deformations, right? But this is the second run of the analysis. First you don't include and check whether you need to include or not, and if you need to include, then you again have two options. One is to use the automated option, some analysis algorithm which automatically accounts in the available commercial programs. Second is the manual option, that you simply multiply your displacement and member forces by 1 over 1 minus theta, right? Then the third case is that your theta is greater than theta max. In that case your structure is potentially unstable and it should be redesigned, right? So in no case you can be having a theta greater than theta max. If you have that case, you have to change your design, right? So there can be a case that when you include the automated analysis in the P delta analysis is automatically included by the commercial program. In that case, the condition theta less than theta max should still be satisfied, right? So in any ways you go for automated inclusion of the P delta effect or not, this condition should always be satisfied, that your theta should not be greater than theta max, right? However, the value of theta computed from this expression, the original expression, is permitted to be divided by 1 plus theta before checking this condition. Let's say that you run the analysis for the first time and you directly include P delta without checking, right? So you still need to consider or check this condition, theta less than theta max. However, that theta now you will not be using this expression to calculate, because you already include P delta effect. So this expression is used when you don't include, and then this can be used to check whether to include or not. But if you already include, then you can calculate theta from this expression, but you divide your value by 1 plus theta, right? So again I repeat that when P delta effect is included in an automated analysis, the condition that theta should be less than theta max should still be satisfied. However, the value of theta which you will be using, which you will be computing from this expression, you need to divide it again by 1 plus theta, right? So let's say that you run the analysis and you compute, you automatically include the P delta effect and you get some values of Px, Vx and delta, because this will be coming from analysis. And if in that analysis the P delta is automatically included, in that case the resulting theta value which you will be calculating from this expression Vx, Hsx, Cd, you again divide that theta with 1 plus theta, right? So if you get this number as 0.2, you again divide this 0.2 with 1 plus 0.2 to get a reduced value, and that should be used to check whether theta is less than theta max or not, right? So please consider all those quick tricks in mind while performing that step by step procedure. So these provisions are all connected. There are always ifs and buts, so you need to consider all of them in totality, not just one provision at a time. So just see one provision, but if there is any exception somewhere else, please consider that also. So this is only when the P delta effect are automatically considered by the analysis program. Then you need to divide your calculated theta with 1 plus theta again to check that condition, right? So one important consideration again related to P delta effect, that even if your first few set of steps tell you that ELF procedure is not applicable, even in that case the P delta effect for modal RSA or for modal response history analysis, they are checked using the ELF procedure, right? So this expression, the last expression, this one, to calculate theta, you have to apply that expression, and in that expression Px, Vx, delta, they all will be coming from ELF procedure, right? So even if ELF procedure is not permitted for your structure, just in order to check that P delta is applicable or not, you have to apply it, right? So even if you have to design it on RSA, but in order to check the P delta requirement for modal RSA or modal RHA, the ELF procedure is required, right? So this please keep that in mind. Yes, you are right that in high-rise buildings we should always go for this particular check, and in most of the cases for high-rise buildings we should include that P delta effect, right? P delta effect is one, you can say, shortcut of a more detailed analysis procedure called large displacement analysis. And large displacement analysis is devised to account for a very you can say obvious kind of nonlinearity type, and which is called geometric nonlinearity. So please go through that idea from different references. What is geometric nonlinearity and how different analysis procedures can account for that geometric nonlinearity. So two basic methods: large displacement analysis and P delta analysis. Large displacement analysis is a more comprehensive analysis. P delta is its shortcut, it's its subset, right? So P delta can account for geometric nonlinearity using some approximate formulation, right? But it is accurate enough for our civil engineering structures. It is as accurate, almost as accurate as the large displacement analysis, right?